Welcome to the video lesson for section 5.1, using fundamental identities. We're going to review a lot of the identities with our trig functions and use them to help us simplify some expressions. Let's get started. In reviewing our reciprocal identities, remember that the sine function can be rewritten as 1 over the cosecant of x, since they are reciprocals. The cosecant function can be rewritten as 1 over sine of x for the same reason. Continuing, the cosine function is the same as 1 over secant of x. The secant is the same as 1 over cosine. The tangent function can be written as 1 over cotangent, and the cotangent function can be written as 1 over the tangent function. All right, we're going to go ahead and find all 6 trig functions. We are given the fact that the secant of our angle is negative 17 over 15. So to begin with, I'm going to go ahead and draw a triangle. Put my angle down here at the bottom as my reference. The secant is going to be the hypotenuse over the adjacent, so I'm going to put a 17 and a 15. And then I do have a negative sign, and we know that our hypotenuse cannot be negative, so I'm going to make this a negative 15. Using my Pythagorean theorem, I can solve for my other side, which is going to have to be an 8. And from here, I go ahead and continue to find the rest of my trig functions. I know for sure the cosine is going to be the reciprocal of the secant, so that's going to go ahead and be negative 15 over 17. I can solve for the sine function using my triangle. It's going to be 8 over 17, which means that the cosecant, being the reciprocal, is going to be 17 over 8. For my cotangent, it's going to be the adjacent over the opposite, so that's going to be negative 15 over 8, which means that my tangent is going to be the reciprocal of that value, which is going to be 8 over negative 15. For our quotient identities, the tangent is going to be able to be written as the sine of x over the cosine of x. And remember that our cotangent is the reciprocal, so it's going to be the cosine of x over the sine of x. All right, looking at our expression here, we're going to use our trig identities, our reciprocal identities, or quotient identities to rewrite the expression and simplify it wherever possible. If you look at our sine function, that's pretty much already simplified. For our cotangent function, though, we could rewrite that using the quotient identity. We would get the sine of x is equal to the cosine of x divided by the sine of x. And then if we simplify here by cross-canceling out our sine functions, we are left with our final answer of just the cosine of x. All right, for our example here, we have cosecant and cosine. If we want to try and rewrite cosecant function, the only process we have right now is our reciprocal identity. So I can rewrite that as 1 over the sine of x. And then we can multiply that by the cosine. Once we multiply those together, we end up getting cosine of x over the sine of x. And then recognizing the quotient identity, this can be rewritten as the cotangent of x. And we have simplified our expression. Reviewing our even and odd identities, for our sine, cosecant, tangent, and cotangent functions, when we take the function of the negative angle, that negative sign gets moved to the front. So we can see that the sine of negative x is going to equal negative sine of x. And then for the same reason, cosecant of negative x would be equal to the negative cosecant of x. And it works the same way for our tangent and our cotangent functions. The tangent of negative x is equal to the negative tangent of x. And then the cotangent of negative x is equal to the negative cotangent of x. For your cosine and your secant, for those, the negative sign just will get taken out because of how things work with our unit circle. So we have cosine of negative x is equal to the cosine of x, and the secant of negative x is equal to the secant of x. Going back and reviewing our Pythagorean identities, based off of the triangle and the fact that sine is our y value and cosine is our x value, and we have a hypotenuse of 1, we see we have our first identity of sine squared of theta plus cosine squared of theta is equal to 1. If we take that identity and we divide it by the sine squared, we end up getting 1 plus cotangent squared is equal to cosecant squared. And that gives us our second identity. If we go back to our initial function, the sine squared plus cosine squared equals 1, and we instead divide that by the cosine function, cosine squared, then we get tangent squared plus 1 is equal to the secant squared. Now remember, the trick for this is anytime we see something that's squared, it's usually going to be a variation of one of these. So you go back to the function that has that term in it, and you want to manipulate it so you can get that term by itself, and then substitute what that term would equal. So for example, if I had something that had just a sine squared, I would look at my first identity here. I would know that to get sine squared by itself, I subtract cosine squared on both sides. And then instead, I would now have sine squared is equal to 1 minus cosine squared, which I can then substitute in to help simplify. All right, we're going to go ahead and simplify this expression, first dealing with our negative angles and then dealing with our functions. So the cosecant of negative x, remember when we simplify that, the negative sign will get pulled out. So we have negative cosecant of x. And then for the cosine of x, when we simplify that, we get simply just cosine of x. And this is very similar to the problem we just did. If we rewrite the negative cosecant of x using our reciprocal identities, we get negative 1 over the sine of x times the cosine of x. When I multiply that together, we have negative cosine of x over sine of x. And if we simplify that, we now have negative cotangent of x using our quotient identities. For our example here, we have sine times cosine squared minus sine. I notice that both my terms here have a sign in it, so I'm going to go ahead and factor that value out. And if I do, I'm left with a cosine squared of x minus 1. Now this one's a little tricky because we know that 1 minus cosine squared of x is equal to positive sine squared of x. But I have the opposite of that now. I have cosine squared of x minus 1. So that's actually going to simplify to be negative sine squared of x, which means I now have sine of x times negative sine squared of x. And if I multiply everything together, I now have negative sine cubed of x. For this example, we're going to use our quotient identities. To begin with, I'm going to rewrite cotangent as cosine over sine. So I have sine of t plus cosine of t over sine of t times cosine of t. I'm going to do two things here. I'm going to multiply my cosines together to get cosine squared. And since I have a fraction, I'm going to go ahead and multiply my term on the left by sine over sine, which will help me combine my terms. So sine of t over sine of t. When I multiply my first expression together, I'm going to get sine squared over sine. And then when I multiply my second expression together, I'm going to get cosine squared over sine. Since my fractions have the same denominator, I can add my numerators together. So now I have sine squared plus cosine squared all over sine. Using our Pythagorean identity, I know that sine squared plus cosine squared is equal to 1. So I now have 1 over sine. And then using my reciprocal identity, I can rewrite that as the cosecant of t. Looking at our next example, one of my strategies is always to try and rewrite things in terms of sine and cosine. And in order to do that here, we're going to rewrite things using our reciprocal identities. So my secant is going to become 1 over cosine. And the cosecant is going to become 1 over sine. And now instead of dividing by 1 over sine, I'm instead going to multiply by the reciprocal, which would be sine of x over 1. And when I multiply that by 1 over cosine, we get sine of x over cosine of x. And then using my quotient identity, that's going to be the same as tangent of x. Looking at our next example, we do have some squared terms, so we might have to use our Pythagorean identities. But I'm going to start off by using my quotient identity and also a reciprocal identity. So I'm going to rewrite the tangent using my quotient identity as sine squared over cosine squared. And then I'm going to rewrite secant as 1 over cosine squared. All right, I'm going to go ahead and multiply by my reciprocal. So instead of dividing by 1 over cosine, I'm going to multiply by cosine squared over 1. And then I can cross cancel some things, cross cancel my cosines, which means that I am left with just a sine squared term as my final answer. All right, for our expressions here, I have a 1 minus sine squared and I have a secant squared. Looking at that 1 minus sine squared and doing my Pythagorean identities enough times, I know they're related. And so if I go back to initial, I have sine squared of x plus cosine squared of x is equal to 1. So taking that initial identity and subtracting sine on both sides, I have cosine squared is equal to 1 minus sine squared. So I now can take my cosine squared and substitute it in, which means my initial expression is now going to become secant squared of x times cosine squared of x. Using my reciprocal identities, I can rewrite secant as 1 over cosine squared times cosine squared. And then I can cross cancel my terms, and I am left with nothing, which means that I have 1 as my final expression. All right, here we have a unique example. I have cosecant to the 4th power minus cotangent to the 4th power. I'm going to go ahead and factor this. Turns out this is a difference of squares, and I can factor it as cosecant squared minus cotangent squared. And then I can multiply that by cosecant squared plus cotangent squared. If we go back to our initial Pythagorean identities, I know that 1 plus the cotangent squared is equal to cosecant, which means if I subtract cotangent on both sides, my first expression here is going to end up being just 1. So I have 1 times the cosecant squared plus cotangent squared. I'm now going to use my reciprocal identities and my quotient identities. Cosecant is the same as 1 over sine squared, and cotangent is the same as cosine squared over sine squared. These have the same denominator, so I can add together my numerators, and I have 1 plus cosine squared of theta all over sine squared of theta. And that is my fully simplified expression. To simplify our expression here, we want to make sure we combine our denominator to get a single term. Right now I have 2. I have 1 and negative sign. So in order to do that, I'm going to multiply both the numerator and denominator by 1 plus sine of theta. And when we multiply this together, it works very similarly to like complex conjugates. What I'm going to get for my denominator is my first term squared minus my second term squared. So I have cosine of theta times 1 plus sine of theta in my numerator. And then for my denominator, I have 1 minus sine squared. Going back to our Pythagorean identities, 1 minus sine squared is the same as cosine squared. So I can rewrite this as cosine of theta times 1 plus sine of theta over cosine squared. And now I can go ahead and cross cancel. My cosine with my exponent's going to cancel. So I only have a single cosine in my denominator. And my final statement's going to be 1 plus sine of theta over cosine of theta. For our example here, we see we have a similar issue with our denominator. I have 1 plus secant, which is 2 terms. I'd like it to be 1. The way we're going to accomplish that is by multiplying by 1 minus secant for our numerator and our denominator. For my denominator, when I simplify, I'm going to get 1 minus secant squared. And then for my numerator, I'm going to go ahead and just leave it. I'm not going to multiply together just yet. Usually when we do this, something will cross cancel at some point, so I'm not going to multiply until I absolutely have to. And then I have 1 plus secant over tangent. If we go back to our Pythagorean identities, I know that 1 plus tangent squared is equal to secant squared. So then 1 minus secant squared is going to equal negative tangent squared, which means I now have 1 minus secant times tangent divided by a negative tangent squared. I can go ahead and do some cross canceling here. I'm going to cross cancel the tangent and the tangent squared. And then I'm also going to go ahead and multiply by a negative 1 over negative 1, which will make this a negative 1 positive secant, and this will become a positive tangent. So essentially I'm moving the negative to the numerator. And then I still have my 1 plus secant over tangent. So I have a negative 1 and a positive 1. Those are going to cancel out. And then I have a positive secant and a positive secant. I'm going to add those together to get 2 secant over tangent. If I rewrite secant, I get 1 over cosine, If I rewrite tangent, then I get sine over cosine. So I'm going to rewrite both, and then I'm going to actually multiply by the reciprocal of tangent. So what that ends up being is 2 times 1 over cosine times times cosine over sine. My cosines are going to cancel. So now I have a 2 and I have a 1 over sine. 1 over sine is the same as cosecant. So I now have as my final answer 2 times the cosecant of theta. All right, for our last example, we have a similar issue here. I have cosecant minus 1, and I'd like that to be a single term. So we're going to go ahead and multiply by cosecant of x plus 1 for our numerator and our denominator. I'm not going to multiply my numerator together just yet. We're just going to rewrite it. So cosecant of x plus 1 times cosecant squared of x minus 1. Remember, for your denominator, we multiply the two things together and we subtract them. So we're going to get cosecant squared of x minus 1. And we can get some stuff to cross cancel here. I have cosecant squared of x minus 1 in my numerator and my denominator, which means for my final answer, I am left with just cosecant of x plus 1. All right, guys, that does it for the notes for this section. Go ahead and get started on the homework. Good luck.